We've learned about neurons and some of the major anatomical parts of the nervous system. We also know that neurons are able to communicate in electrochemical impulses. What we don't know is how neurons are able to conduct and transmit these signals through the nervous system. Chapter 4 will introduce us to this. This is an overview of the topics that we'll cover in Chapter 4. For this specific module, we will limit ourselves to understanding resting membrane potential. The complexity of neural conduction and synaptic transmission can only be understood if we understand membrane potential. You will learn in this module that although the term resting potential is used, there really is nothing restful about everything that's going on in the background, even when a neuron is off or not firing. To understand membrane potential, we have to understand what membrane is, and as you may remember from Chapter 3, we looked at the membrane being the surrounding tissue around the neuron. You see, we have the dendrites here, and the membrane would be on the outside of the neuron. Inside would be the nucleus and various other organelles. You may also remember that the membrane is composed of lipid and protein. More specifically, a bilipid layer. You may remember that that is made up of, or it has two different types of protein, channel protein and signal protein. In this chapter, we will learn about how those walls, those protective coatings in here, facilitate for the transmission of signals in the nervous system. Membrane potential is the difference in electrical charge between the inside and the outside of the cell. To record the membrane potential, one tip of electrode is positioned inside the cell, whereas another tip of another electrode is positioned outside the neuron in what we call the extracellular fluid. To avoid severely damaging the membrane, microelectrodes are used to record intercellular charge. The tips of microelectrodes are less than 1,000 of a millimeter in diameter, much too small to be seen by the naked eye. When both electrode tips are in the extracellular fluid, the voltage difference between them is zero. However, whenever we put one microelectrode inside and the other one outside, then we're able to read what we have as a negative charge, and it is what we call the resting potential that has a steady potential of approximately 70 millivolts, negative 70 millivolts. This would occur when this is what we would call as a polarized neuron. And every time you hear the word polarized, it means that it carries a charge. It has the potential to then act on and demonstrate its force. We'll talk about this a little bit more in future slides. As you already know, when a neuron is off, it has a negative charge, approximately negative 70 millivolts charge. Ions, which are atoms or molecules with a net electric charge due to the loss or gain of one of or more electrons, are what determine whether something is positively charged or negatively charged. The ions that we'll be looking specifically at here are sodium, which are positively charged, and that's what you'll see as Na+, potassium, K+, chloride. You can see that this is an anion, which is a negatively charged ion, and then other organic anions here. In resting potential, we know that exists because the ions are concentrated on different sides of the membrane. We know that when the cell is off, meaning it's not firing, there are more sodium ions outside the cell than they are inside. You have fewer sodium ions inside the cell. And we also have more potassium ions inside the cell than we have outside the cell. Please note that in my attempt to provide this for you here, we have the membrane. This would be one of the lipid layers, and this would be the other lipid layer. And here we would start seeing pumps, what we call pumps. These pumps are specialized proteins, channel proteins, through which sodium and potassium, respectively, come in and out of the cell. Here we can appreciate an artistic rendition of a typical cell membrane, and you can see and appreciate the signal proteins, which are here. You may remember that, and if not, you may look back to chapter 3 to understand this further. And here you can see the channel proteins through which ions enter and exit the cell. So on one side would be the outside, and on the inside would be the inside of the cell. The term resting potential is quite misleading, as there is a lot of activity going on when the cell is off. We know that sodium ions are actively transported to maintain a resting potential, and these are transported through specialized channels, channel proteins, where we see a constant exchange of 3 sodium ions from inside of the cell for 2 potassium ions that are outside of the cell. So you will constantly see this one going out, you have these going out 3 at a time, and then for every 3 that come out, you put 2 of these inside. And this is all occurring through what we call the sodium-potassium pump. Please note that this actively uses energy force that exchanges these ions, and this is basically what depolarizes the cell. You may remember from just 2 slides before that polarization basically means that the cell carries a charge. When you depolarize a cell, that means that the cell no longer carries a charge. Please note, it is important for us to know that what we just described in this slide is a neuron at rest, meaning resting potential, where the cell is polarized and it is capable of charging and then firing. This is all that's happening, all while the cell is off. Here we see a nice rendition also of the neural membrane as it passively and actively is influencing the distribution of sodium, potassium, and chloride, which is the negatively charged ion here in an ion. And this is all occurring across the neural membrane. You can see the first step here where ions in motion move down their concentration gradients. Thus, sodium will tend to enter and potassium will tend to exit. You may remember we talked about this, and that there are 3 sodium ions inside the cell that are exchanged from the inside for 2 potassium ions outside the cell. As you would have experienced with magnets before, you know that positive and positive tend to repel one another, whereas opposites attract. And so when you have too much positivity in one, they will constantly be moving out, in and out of the cell to maintain the balance in there. In step number 2, we see the negative internal charge creates pressure for both sodium and potassium to enter. So whenever you have a negative presence inside from anions, that would be the negatively charged, and typically we see chloride maintaining equilibrium with these two, then these would be attracted, because since there's negativity inside, then you'd see both sodium and potassium entering inside to try to balance things out. In the third step, we would see sodium-potassium pumps, which are specialized channels. Notice that each of these right here, sodium has its own channel, potassium has its own, potassium has its own, and sodium has its own. But this right here demonstrates what we call the big pump, the big channel protein, and that is the sodium-potassium pump. This transports 3 sodium outside for every 2 potassium that they transport in. And just like that, we've described the resting membrane.